This final lecture for Chapter 20 involves the characteristics of batteries and a little bit on electroplating, and there's a calculation at the very last slide that we'll have to learn how to do. So we'll cover Part 3 of the lecture on the characteristics of batteries. A battery is simply a portable, self-contained electrochemical power source, and it contains one or more voltaic cells. Now there's a positive end of the battery, and there's a negative end of the battery. The positive part's called the cathode, the negative part's called the anode. Now if you want to generate 9 volts, you're going to have to link multiple cells together, since no single redox reaction will give you an E0 equal to 9 volts. I think the most is around 6 or so volts. So you have to link them together. Now there's a couple definitions that we need to cover. A primary cell is a voltaic cell or a battery that cannot be recharged, and a secondary cell is a battery that is rechargeable. On the next page we look at a common car battery. A car battery produces 12 volts, so you know you're going to have to link some batteries together. It's called a lead-acid battery. At the cathode there's lead dioxide, and here's the reaction. Now my students don't have to know this reaction, but I would expect them to be able to label the oxidation numbers and to figure out how many electrons are gained. At the anode there's a lead plate. Now in the cathode reaction you have lead dioxide turning into lead sulfate, and then at the anode you have the pure element lead turning into lead sulfate. So each reaction produces lead sulfate. The overall chemical reaction when you add them up is shown below, and for some reason on this PowerPoint presentation the V's, the letter V in these sentences kind of gets shifted, so I hope that doesn't disturb what you're looking at on the screen. But anyway, the overall reaction you can see below. And when you do the cathode reaction minus the anode reaction, you end up getting a voltage of around 2 volts. And so you're going to have to link some of them, that would be 6 of them together, to make an overall 12-volt battery. And you have to separate the anode from the cathode reactions with wood or fiberglass spacers to prevent the electrodes from touching each other, and that would be a short circuit, and then you wouldn't have any productive electricity being produced. On the next slide is simply a picture of the lead-acid battery. Lead-acid batteries can be recharged. As you should know, you can recharge a car battery, and the sulfuric acid electrolyte decreases in concentration as the battery discharges, and when you charge it up it increases as the cell is run in reverse. And sulfuric acid is much more dense than water, and so you can figure out the density or specific gravity of the sulfuric acid to see if it needs to be recharged. So if the specific gravity is between 1.25 and 1.3, then it's charged up and ready to go. But if the specific gravity or density of the sulfuric acid gets too low, you need to charge it. Now these batteries are called wet cells because the electrolyte is actually a liquid, it's sulfuric acid. Now there are dry cell batteries, which we're most familiar with. They're called alkaline batteries. The most common non-rechargeable battery is this alkaline battery. And powdered zinc metal is immobilized in a gel, and it's in contact with a concentrated solution of potassium hydroxide. And so this alkaline solution, or this basic solution, is where the battery gets its name, the alkaline or basic solution. Now the electrolyte is a base, and that's what I just mentioned, and since the electrolyte is a paste, it's not a free-flowing liquid, it's called a dry cell. So wet cells have sulfuric acid in them as a liquid, that would be a car battery, and the dry cells are like your regular old AAA batteries. The reaction at the anode is shown below, and the reaction at the cathode is also shown. And again, the students don't need to actually memorize what the reactions are, they would just need to figure out which one is acting as the Leo reaction, which one's the Ger reaction. Now if you take the Leo minus the Ger minus the Leo, the E0 value, the cell potential for these batteries is around 1.5 volts at room temperature. And here's a little picture of a battery that would maybe be in a watch or something like that. Now there are other batteries. The common rechargeable battery called a nickel-cadmium battery has a reaction at the cathode with nickel hydroxide solid turning into more common nickel hydroxide, and the reaction at the anode is shown below as well, cadmium going to cadmium hydroxide. And again, the students don't need to memorize these reactions, I'm just showing them for kicks and giggles. The cell potential of this nickel-cadmium battery is around 1.3 volts at room temperature, and one of the problems with these rechargeable batteries is that if people throw them away, it's kind of dangerous for the environment because cadmium is a toxic heavy metal. So it's better to recycle them. There are other rechargeable batteries that have been developed. Nickel metal hydride batteries are pretty common nowadays, and lithium-ion batteries are really good because they're very lightweight, and so they pack a lot of energy density in a smaller lightweight battery, and these would be used in cell phones. Now, corrosion is the next topic in this presentation, and it's an example of an undesirable redox reaction, and so it's basically the rusting or the corrosion of metals. A metal is attacked by a substance in the environment, and then it's turned into an unwanted compound. Now, we're going to consider the rusting of iron first, and since the E reduction potential of oxygen is greater than the E reduction potential of iron 2 ions, then iron, the metal, can be oxidized by oxygen that's in the air. So the reaction at the cathode is oxygen turning into water, and the anode reaction, where it loses electrons, is the iron turning into the iron with a +2 charge. Now, the dissolved oxygen is usually in water, and it causes the rusting of the iron. So the iron 2 ion that's initially formed from the rusting of the pure metal iron can further be oxidized into iron 3, which forms the Fe2O3 ion, and there's some water molecules stuck to the crystal, but that's the rust, and then it falls off, and then you have more iron exposed, which turns into iron 2, which transforms into iron 3, and then it forms more rust, and the reaction goes on and on and on. Now, the oxidation occurs at the site with the greatest concentration of the oxygen. Now, there's other factors that will speed up the rate at which iron rusts. pH will change the rate at which it rusts. The presence of salts, like if you're in a seaside location like in Florida, your car is going to rust a lot faster because of the salt in the air. Stresses on iron, like on a bridge, when it's under stress, it can cause rusting to occur faster. And if it's in contact with other metals, you might get rusting of the metal a little quicker than normal. And here's a little picture of the cathode reaction and the anode reaction occurring in a droplet of water as it's sitting on top of a chunk of iron. Now, if you want to prevent the corrosion of iron, you can paint it to keep it away from the oxygen in the air, or you can coat it with another metal, and it would be good to keep it away from water. Now, the way of protecting iron by coating it with another metal is sometimes called cathodic protection. So there's a cathode reaction that kind of protects it. The coating of iron with a layer of zinc is called galvanized iron, and it protects iron from corrosion even after the surface coat is broken. So as long as the zinc is in contact with the iron might be exposed to the oxygen in the air, but instead of the iron rusting, what happens is the zinc rusts first. So zinc has a more negative E reduction potential, which means it wants to be the Leo reaction more than iron wants to be the Leo reaction. So it will actually lose the electrons before the iron does. So zinc rusts, or zinc oxidizes, rather than the iron. And zinc is what's termed as the sacrificial anode. Zinc is sacrificed instead of the iron. So zinc is slowly destroyed, and the iron is still acting as the cathode where oxygen is reduced. And you can use something similar to protect underground pipelines, and that's what's shown on the next page. Often magnesium is used as a sacrificial anode because it has a really negative E reduction potential. And here's a little picture of zinc protecting iron. The zinc is getting eaten away, and the iron is the place where the electrons are going into the oxygen. And here's a picture of the underground pipe being protected by magnesium. Now, one of the things I learned when I was watching TV one day on PBS, it was some home building show, and they had a hot water heater tank, and they cut it open to show that there's a sacrificial anode in your water heater. So that's another example of cathodic protection, or sacrificial anodes. Now, electrolysis is the next topic, and it's possible to cause a non-spontaneous redox reaction to occur, but you have to drive it by an outside source of electrical energy. So what we're going to do, instead of a redox reaction occurring spontaneously, we're going to force one to occur backwards. We're going to pump in electricity and cause the redox reaction to occur. And these reactions are called electrolysis reactions, and they take place in what's called an electrolytic cell. Now, in a voltaic cell or an electrolytic cell, you still have reduction occurring at the cathode. So there is still the GR at the cathode, and there's still oxidation at the anode. But the electrons are forced to flow from the anode to the cathode, and which is normal, but the freaky thing is that the anode is positive instead of being negative as in a normal battery, and the cathode is negative. So you're basically still having electrons flowing from the anode to the cathode, but you're forcing them to go from the positive to the negative, which is the anode is positive in the example, and the cathode is going to be negative. And I'll show you a picture of the battery or the electrolytic cell on the next page. So in a voltaic cell, the anode is normally negative, but now it's positive, and the cathode is positive instead of negative. And here's what it looks like. So here we have molten sodium chloride, and you're going to pump electrons from the anode to the cathode by a voltage source, and the anode is positive and the cathode is negative, and at the anode you still have losing electrons, so chlorine ions are going to turn into chlorine gas, and at the cathode you're going to have the gaining of electrons, so sodium ions in the molten sodium chloride liquid down there is going to turn into the sodium liquid. So you can take a look at this reaction as a good example of what an electrolytic cell does. On the next page, I just write out the cathode reaction and the anode reaction, showing the electrons being gained and the electrons being lost. Now, a battery or some other source of direct current is going to act as an electrical pump, and it's going to push the electrons to the cathode, and it's going to pull them out of the anode. And you have solid sodium being produced at the cathode, which again is negative in this case, and additional sodium ions would migrate in as the sodium solid is being produced, and then you have chlorine gas being produced at the other one. And industrially, electrolysis is used to produce metals like aluminum and gases like chlorine. In fact, aluminum oxide, also called bauxite, is a white powdery substance that they dig up from the ground, and they zap it with a heck of a lot of electricity, and then molten aluminum flows out of it, and then oxygen bubbles off. So usually next to aluminum plants where they manufacture like aluminum, pure aluminum, you have huge amounts of electrical needs, so they build power plants next to the aluminum plant. Now, the electrolysis of aqueous solutions is slightly different. Do you get the same product if you electrolyze an aqueous solution of salts? Well, the answer is no, because water complicates the issue. So we're going to consider the electrolysis of sodium fluoride, an aqueous solution of sodium fluoride. If you look at the cathode GUR for sodium ions and the cathode GUR for water, you can see that water has a more positive reduction potential, which means water would rather be reduced than sodium ions if they're next to each other. So thus water is more easily reduced, and that's going to produce hydrogen. And at the anode, the fluoride ion is trying to turn into fluorine gas, but water is also trying to turn into oxygen. So if you look at the reduction potential for the Leo reaction, the water has a more positive reduction potential. It has a less positive reduction potential, which means it's going to be losing the electrons more readily than fluoride ions losing electrons. So basically what happens is that you end up getting the oxidizing of water rather than the fluoride ion. And so at the cathode you produce hydrogen gas, and at the anode you produce oxygen gas. So at the cathode, which is negative in this case, you have hydrogen gas bubbling off, and at the anode, which is positive in these electrolysis examples, you have oxygen gas bubbling off. Now you have something called an active electrode defined on the next slide. Electrodes that take part in electrolysis are called active electrodes, and an example of an active electrode is the process called electroplating. So if you consider this example, you have an active nickel electrode and another metallic electrode, for example steel, placed in an aqueous solution of nickel sulfate. What happens is at the anode you have nickel solid turning into the nickel ions, and at the cathode you have nickel ions turning into nickel solid. Now, this doesn't have any E value when you calculate the GUR minus the Leo, because it's obviously the same reaction occurring, just in reverse. So in order to get this reaction to occur, you need to pump in electricity. But what happens is that you have nickel transferred from the anode into the cathode compartment, and that's going to plate on this active electrode. It's going to be placed on the other metallic electrode, which is the steel. The active electrode is the nickel. And again, you'll need to push the reaction along with some electricity. And electroplating is an important protection process to keep objects from corroding, such as stainless steel. Steel is coated with nickel, and then it's protected from rusting. So it's sort of like the sacrificial anode concept, except the nickel isn't going to rust unlike, iron would. So here's a picture of an active electrode. So here we have our nickel solution. We have nickel at the anode, and we have a metallic cathode like steel, but the ions in the solution are going to be plating the metallic cathode. So you're pumping electrons from the anode to the cathode, and you're basically transferring the nickel from the anode onto the cathode, and that's called electroplating. Now there's a quantitative aspect of electrolysis that you have to calculate. This is going to be the last little topic of the chapter. So if you want to know how much material you can transfer from the anode to the cathode, you have to do a conversion. So we're going to consider the reduction of copper ions into pure copper. Now, you can clearly see from the formula that in order to change copper ions into pure copper, you have to use 2 moles of electrons. So 2 moles of electrons will actually plate out 1 mole of copper. So using this information as well as the following conversion factors, you can calculate how much copper will be plated after a certain amount of time given a certain amount of current. The conversion factors we're going to use is 1 mole of electrons is 96,500 coulombs, also known as 1 Faraday, and 1 amp of current, or 1 ampere of current, it depends on how you want to pronounce it. 1 amp is the same thing as 1 coulomb per second. So that's the amount of electricity that you're going to be using. So we're going to look at this conversion problem on the next page. So it's going to be a 5-step conversion problem altogether. So we want to know how much copper in grams is going to be obtained from electrolysis by using 3.5 amps for 5 hours. So the first thing we need to do is figure out how many coulombs that we're using. So we're going to use the 3.5 amps, which is the same thing as 3.5 coulombs per second, and we're going to multiply it by the number of seconds there are in 5 hours. So using some conversion factors, you can calculate how many coulombs of electrons that you're using. So it's 63,000 coulombs of electrons. So then you're going to convert the coulombs into grams of copper. So we have 63,000 coulombs, and we're going to change it into grams. So we know that in 1 mole of electrons there's 96,500 coulombs. So we're less than 1 Faraday, by the way. And then you're going to change the moles of electrons into the moles of copper, and this is where the factor of 2 comes in. We know that copper had a 2 charge, so if you're going to be changing copper ions into pure copper, it's going to take 2 moles of electrons for every 1 mole of copper. And after you get moles of copper, you can just convert it to grams by using the mass on the periodic table, and you get your final answer. So it's going to take 5 steps altogether, 5 conversion factors altogether, and I broke it up into 2 parts, but you could actually do it in one gigantic conversion. So it ends up being 20.7 grams of copper.